LiSA, the Liquid Sunlight Alliance, is embracing the ambitious challenge of direct generation of liquid solar fuels.
Our vision is to establish the science principles by which coupled microenvironments can directly generate liquid fuels from sunlight, water, carbon dioxide, and nitrogen.
At Caltech, LiSA has key facilities for the Hub project. These include facilities and resources for accelerated discovery of materials and durability, resources for design and prototyping of solar fuels systems, and laboratories that are focused on investigation of selective catalytic processes.
The science team is diverse demographically, bringing a wide range of experiences and backgrounds in addition to their scientific expertise to the team.
And we also have researchers working collaboratively in the space of Jorgensen. So we're all sharing the same environment and working on these problems in the same space.
Lab is interested in converting abundant and inexpensive precursors like carbon dioxide, dinitrogen, ethylene into more valuable products.
Ethylene is essentially the second largest commodity chemical made industrial on planet Earth. So it's an enormously valuable product. We currently get it by cracking oil through a process that ultimately leads to it. And it would be fantastic if we could use CO2 from the atmosphere to generate this incredibly useful commodity chemical.
I do the electrochemical conversion of carbon dioxide to fuel sources. What that entails is taking CO2, water, electricity, and then ideally sunlight later on to mimic photosynthesis. And what I can do is use an electrochemical cell and probe this while it's being used to understand how we're making these products. And based on what I can find, I can change my catalyst to maybe change the performance so we can steer it more towards liquid products such as ethanol, which is a direct fuel source.
The kind of main goal that HCE is doing is looking at solar fuel liquid catalyst. We draw inspiration from traditional chemistry techniques and traditional chemistry analytical techniques. And what we do is we miniaturize those, we parallelize them, and then we automate them.
We have these electrochemical cells that we put these different membranes and electrodes and things in, and we can kind of develop them in different ways. I make these membranes out of multiple layers of polymers, and sandwiched in the middle, I have nanoparticle catalysts. And then in order to test those, we use what's called a potentiostat, which allows us to apply a potential and measure the current, or vice versa. We can apply a current, measure potential, and start to understand how these cells are performing.
CO2 reduction is an incredibly important field, and we're looking to improve the catalysts that exist by introducing a molecular film on the surface of that electrode. I'm putting together my gas diffusion electrode cell, which enables us to evaluate the activity and selectivity of whatever catalyst we are testing. And we're able to do this in air as well as in a glove box, which is a pretty unique feature of our lab.
Our group's interest is investigating the geometric and electronic structures of the reaction intermediates that take place when we're doing the CO2 reduction process. And combined with all of this instrumentation that we have access to, we can comprise a complete picture of what the mechanism for this molecule looks like.
What our group does is we focus on copper as an electrocatalyst. It's very good for making carbon-carbon bonds. And what we do is we take a gas diffusion layer, which is basically like a carbon felt. It's very porous. And we do a process known as sputtering. And what this does is deposits a very thin layer of copper on top of it. So I'll take a sheet of this and put it into one of my electrochemical cells. And in this cell, I'll be running carbon dioxide through it. And so on one side, we're reducing carbon dioxide to fuel products. On the other, we're making oxygen gas simultaneously. So this mimics photosynthesis.
We want to have a catalyst that is going to produce something very efficiently, very easily. We want it to be selective so that it only produces one thing in particular. We don't get nasty byproducts that we don't want. And it needs to be durable and stable. It needs to be able to produce that one very specific fuel very efficiently, and it needs to be able to do that for a long period of time in the relevant environments. We've got a bunch of inkjet printers. We have replaced the ink heads with metal ink atomizers. And so instead of printing yellow, magenta, black, we're going to be printing iron, tungsten, molybdenum, all different kinds of metals. And they're going to print directly on these glass plates that you see. We have these big tube furnaces that we're able of controlling the temperature, controlling the gaseous environment around these metals. And depending on what we do to them and how we process them, you'll get different structures, different functions, and different activities from each of the metals on these plates.
Here at LiSA, we have a wide range of instrumentation we use for our research.
We use a SRI gas chromatograph,
which allow us to measure the gas that is output from the cells.
And liquid chromatography to measure our liquid products.
We have what we call an analytical electrochemistry instrument. What it does is take the traditional analytical chemistry techniques of gas chromatography and high-pressure liquid chromatography and combines them with the actual analytical cell itself.
The HPLC takes our electrolyte and is able to analyze the liquid products that we've made during our reactions. And so that gives us an idea of how much of each product that we've made exists in the electrolyte.
We now have very specialized instruments that instead of printing on glass, we can print on essentially woven fibers of carbon. Now, these carbon called gas diffusion electrodes are very useful for some of the products that LiSA is interested in making. So here we have what we call an electrode deposition system, which was made specifically for depositing these materials onto these gas diffusion electrodes.
One unique piece of instrumentation that our group has access to is called ultrafast transient absorption spectroscopy. It operates on the femtosecond timescale. And what's interesting about that timescale is we're actually getting down to the timescale of molecular dynamics.
So I'll use a lot of imaging techniques such as scanning electron microscopy, where we can look at these materials at the nanoscale and actually understand the surfaces and what's occurring in the materials.
So we can go and do what's called X-ray fluorescence, and it's literally going to tell you the ratios of atoms within your sample. That's just the composition. If you want to know the structure of it, we do something called X-ray diffraction. That's going to show you the exact crystal structure, and with both the crystal structure and the composition, you now have a very well-defined material which you can now experiment on and define what its functions are.
Another piece of instrumentation that's really unique and special to our lab is this instrument called magnetic circular dichroism. And the purpose of that instrument is we're using polarized light to allow us to definitively assign electronic transitions within a molecule. And the consequence of that is it allows us to definitively understand and assign the electronic structure of a molecule that we're looking at.
We also have chemical fume hoods that allow us to do different types of material synthesis, as well as depositing materials and making the electrolytes that we use to flow through our cell.
What's really great about the LiSA project is we're building off of 10 years of artificial photosynthesis research that's already been done at Caltech. So I feel like this is just a step in the right direction and something that Caltech is already really known for.
It's an incredible opportunity to be part of LiSA. It's been incredible. The faculty here at Caltech and the other faculty at the associated institutions we're collaborating with, they just, the agility of the group, if you take it in its sum, is really breathtaking.